This is part 3 of the Chapter 8 lecture notes. I kind of moved ahead a little bit. Sorry, I'm trying to get my pointer working, but I kind of moved ahead a little bit to this slide here that shows you all of the conditions or the major conditions that lead to the resting membrane potential. So we'll start with the leak channels. Let's talk about leak channels first. A leak channel allows for certain ions to diffuse across the plasma membrane. So they will diffuse in the direction, they will diffuse down their concentration gradient from high to low concentration. So let's look at the potassium leak channel. Potassium ions are shown here as the orange molecules with the positive charges. And you can see that there's a much higher concentration of potassium inside of the cell, inside of the neuron. And so when it encounters a leak channel for potassium, it's going to move from where its concentration is high to where it's low outside the cell. So if you have potassium constantly leaking out, and this resting membrane potential depends on potassium being high inside the cell, you need a pump to pump potassium back in. And that's where the sodium-potassium exchange pump comes in. Now, the sodium leak channels work the same way, but sodium concentration is higher in the extracellular fluid. So it's high outside the cell. When it encounters a leak channel, it's going to diffuse back into the cell where its concentration is low. So in order to keep sodium high outside the cell, the sodium-potassium exchange pump pumps sodium out. So the sodium-potassium exchange pump is helping to maintain this negative 70 millivolts. It's helping to maintain the resting membrane potential. One of the factors that keeps the resting membrane potential negative, so more negative inside the cell than outside, is the fact that more positive ions are being pumped out than in. 3 sodium ions are pumped out and only 2 potassium are pumped in. So you're pumping out more positive. That makes it more negative inside. Think about that for a minute. If you're removing positive, then the voltage will be more negative. So we're removing more positive ions, then that's going to help the inside of the cell be more negative. But the other thing, which is a huge factor in the negative inside of the plasma membrane, are these negatively charged proteins. These proteins can't get out of the plasma membrane, so they're going to keep the inside more negative than the outside. They're not found in the extracellular fluid. Now, this is explaining what I just explained to you, so you can read that on your own if you want. So now we're going to talk about changes in the membrane potential, because it's these changes that lead to a nerve impulse being transmitted from a neuron to a target. So what can change the membrane potential? There are, now we have channels that are gated. And so if we open those gated channels, if we open a sodium channel, for example, if we open a sodium channel, we're going to have more sodium moving into the plasma membrane. And sodium is positively charged. So that negative value on the inside of the membrane is going to become more positive. When that happens, when the negative 70 goes in a more positive direction, that is called depolarization. And it often happens because channels open up for sodium and allow sodium inside the cell. They're kind of like leak channels, but they're closed some of the time. Leak channels are always open. Now, potassium channels, when potassium channels open, the opposite thing happens. Because if a potassium channel opens that allows potassium to move across the membrane, we've already talked about potassium is going to move out. It's going to diffuse out of the cell. And that's going to cause, since potassium is positive and you're losing positive charge, it's going to make the membrane potential more negative. And that is called repolarization. And then if you go even more to more negative than -70, so like -80, -90, that is called hyperpolarization. But anytime just to summarize this, anytime the membrane potential becomes more positive, that's depolarization, and opening sodium channels can cause that. Anytime the membrane potential becomes more negative, it's repolarization or hyperpolarization, and opening potassium channels can cause that. Now, we talked about resting potential. Now we're going to talk about graded potentials or local potentials. And these happen either in the dendrites or the cell body of the neuron. These occur in the dendrites, across the plasma membrane of the dendrites or the cell body. And a graded potential can lead to an action potential. Okay? Action potentials occur in the axon of neurons. And an action potential in a neuron is called a nerve impulse. And the only way for an action potential to occur is for the neuron first to depolarize. The axon has to depolarize. In other words, sodium has to come in. And sodium has to come in enough to cause that potential to reach threshold. Threshold for a neuron is somewhere around -55. And this shows you the steps in the generation of an action potential. You will need to know these. You will need to understand what happens in the generation of an action potential in a neuron. You need to understand that it happens right here at the axon hillock, which is the beginning of the axon. And you can see over here the graph, like each step is described, and then it's shown in the graph of voltage. So this voltage is -70, and that's the resting potential. And you can see that threshold is, they've got it as -60, which is fine. So -70 millivolts is resting potential. If a graded potential causes depolarization to -60, that's threshold. And once threshold is reached, an action potential will be generated. And that's when depolarization goes all the way as high as +30 millivolts. Okay, so step one is depolarization to threshold, and that's going to happen by a graded potential either along the dendrites or the cell body. That potential is going to cause a voltage change in the positive direction. And if that voltage change is large enough to stimulate the axon, to cause the axon to depolarize to threshold, then an action potential will be generated. So the first step is depolarization to threshold, and that means that enough sodium has to come in to cause that potential to go from -70 to -60. Then step two is activation of sodium ion channels and rapid depolarization. So now we have voltage-gated channels, is how I've always learned them. Sodium voltage-gated channels, as you can see here, open up, and sodium rushes into the cell, and that causes the potential to go in, to very quickly go to 0, and then 10, 20, and then in step 3, it reaches as high as 30 millivolts. And that's going to be as high as the action potential is going to get. And then the sodium channels are going to inactivate. And when they inactivate, no more sodium can come in. And the potassium channels are going to open. And potassium is going to start to move out of the cell. And when that happens, now your voltage is going to go into a more negative direction. And because the closing of the potassium ion channels happens kind of slowly, Once the voltage gets to negative 70, it will probably hyperpolarize and go maybe even as far as down to negative 80 or 90. But then after a certain amount of time, it will normalize out to negative 70 again. So here's negative 90 millivolts. That comes from hyperpolarization. But then after a short amount of time, it will equalize back out at negative 70 millivolts. Okay, some definitions you need to know for action potential. First of all, an action potential is an all or none event. And that means that if the stimulus or graded potential brings the membrane of the axon to threshold, there will be an action potential, and you'll either have an action potential or you won't. It's all or none. There are no stronger action potentials. There are no action potentials that are weaker or stronger than others. They're all the same strength. They all go to positive 30 millivolts. And so if that membrane reaches threshold, the action potential will propagate or travel down the length of the neuron all the way to the end of the axons, to the axon terminals, and to the target. Okay. The refractory period is the time from when the voltage-gated sodium channels open, which is depolarization, rapid depolarization, until repolarization is complete. The membrane can't respond to further stimulation during that refractory period. And these are the steps of the action potential. I'll read through them. The action potential begins at the axon hillock, which is the beginning portion of the axon. And what happens is step 1, the membrane depolarizes to threshold, which is negative 60 millivolts. And what causes this are graded or local potentials that are generated along the dendrites or the cell body of the neuron that lead to opening of sodium channels at the axon hillock. And as if enough sodium comes in at the axon hillock to reach negative 60 millivolts, then there will be an action potential. So once that negative 60 millivolts is reached, voltage-gated sodium channels open. And they're voltage-gated because that voltage of negative 60 is what causes the channels to open. So the sodium channels open, sodium rushes into the cell, depolarization is very rapid, and it leads to an action potential as high as that goes all the way to positive 30 millivolts. Now, at the positive 30 mark, the voltage-gated channels close, the sodium voltage-gated channels close, potassium voltage-gated channels open, and they respond to that positive 30 millivolts. And that's going to repolarize the membrane or cause it to go in a more negative direction. And then the potassium channels will close and the membrane will return to resting potential at negative 70. These are the steps. Action potentials can be continuous if the axon does not have myelin. If it's unmyelinated, the action potential is continuous, and that's going to be relatively slow. I mean, all of these impulses are fast, but it's slower if the action potential occurs in unmyelinated axon fibers. But we call it saltatory propagation when we have myelinated axons, and those are much faster nerve impulses. And I just want to show you a picture. So basically, here's an unmyelinated axon, and the action potential must propagate all the way down the length of that axon. Whereas if it's myelinated, saltatory means it can jump. And it's going to jump from here at the axon hillock to node of Ron VA, node of Ron VA, node of Ron VA, node of Ron VA. That's what those little places that are not myelinated along that axon are called. So it's going to jump. That's why we call it saltatory conduction. And that is a much faster nerve impulse than if it were unmyelinated.